You know what happens when you drop something? It starts accelerating down. But what happens if you drop light, or shine it downward? It's already moving at the speed of light, so it can't move faster. Einstein predicted that it actually changes color, but nobody knew if he was right. Here, where I work, an ingenious experiment was done to test this.
So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly.
Einstein predicted a different kind of redshift, a redshift that occurs as light moves up in a gravitational field.
Let's talk about the Doppler shift and time dilation that can occur because of gravitation. And we'll understand this using the equivalence principle that we were just introduced to. So the equivalence principle actually can allow us to calculate a Doppler shift, and recall that a Doppler shift is a change in frequency that light, or electromagnetic radiation in general, undergoes when traveling through a gravitational field. So let's again consider an accelerating reference frame with a light wave sent from the floor of that reference frame to the ceiling. All right, so let's imagine our reference frame here is in a rocket again. We're going to send light from the floor sent to the ceiling. The height that the light will travel is a distance h. And this is a rocket's frame, so it's going to be accelerating. And the change in velocity of the rocket, by the time that, because it takes a finite amount of time for the light to go from the floor to the ceiling, the rocket will have accelerated in that time. And so its change in velocity will be just acceleration. Let's say it's constant acceleration a times t, the time it took for the light to go from the bottom to top. That's how much the velocity will have changed. That's delta v. But you can think of it, therefore, that that's the velocity of the ceiling when the light gets there, relative to the velocity of the floor when the light was first launched. The light was launched upward. The rocket frame was accelerating, so it's increasing its velocity. And by the time the light reaches the top, the ceiling's moving a bit faster by a times t. So the light is detected by a detector at the ceiling that is moving at some velocity v relative to the floor, effectively. Now, for accelerations acceleration times time much less than the speed of light, then we can approximate the time it takes for light to get to the top of the rocket's reference frame is just h over c, the height over the velocity, which is the speed of light. And then there'll be smaller terms due to the finite time it took. And what they're trying to say is effectively, by the time the light reaches the ceiling is effectively receding, moving away with a velocity relative to the floor, with a velocity which is a times t, but time is just the height of the rocket, the distance light travels over the speed of light, so it's a h over c. So that's the effective velocity, or the velocity difference of the ceiling relative to the floor. But you can think of it as the velocity of the rocket when the light was first emitted, and then the velocity of the rocket when it was detected, and there was a difference in velocity there. The velocity increased. And that was a h over c, where a is the constant acceleration of the rocket, h over c is the time it takes to go from the floor. Now, from the previous slide, we saw that the ceiling is receding, and we calculated the velocity, the relative velocity difference of the ceiling with respect to the floor when it was emitted. So we can work out the velocity that we should put here in this formula for the Doppler shift, right? That was just a, the acceleration, times h over c. Right? A times time, where time was h over c, the distance over velocity. So we can do that. Let's plug that in. So delta f over f naught is minus a h over c. And remember, that was over c again right here. So it's minus a h over c squared. Which, now, if I say this accelerating frame is equivalent to a frame which has gravitational acceleration, and I set a equal to the acceleration due to gravity on the Earth's surface, little g, then that's telling me that the change in frequency, delta f over f naught, that relative change in frequency, is minus little g times h over c squared. What that means is, in a non-accelerating frame, but in a frame which has gravity, i.e. the surface of the Earth, and I have an emitter of light sending the light, say, upward, and it goes up a distance h, and I detect the frequency after it's gone up a distance h, I will detect a change in the frequency of that radiation because of the Doppler shift, using the equivalence principle relating the accelerating frame to this gravitational frame. And so that's an important result. That's telling me that light that's being emitted from deep inside a gravitational well, like on the surface of Earth, going up, is changing frequency. Now, it turns out this is a very small change, at least for Earth. Nevertheless, it was measured. So this Doppler shift for light in the gravitational field at the surface of the Earth was tested by Pound and Rebka in 1959 using gamma rays. And they had a source of gamma rays and a detector on both above and below a tower. So you can send the gamma rays, say, from the top of the tower down or from the bottom of the tower on up and detect them. Now, the tower they used had a height of 20 meters, and sending the gamma rays down means dropping the photons, if you like, to the ground where you have your receiver. And they can measure the frequency shift. And that calculated frequency shift and what they're trying to measure, delta f over f, for a 20-meter height, plugging in the speed of light squared in the denominator and the acceleration due to gravity of 9.8 meters per second squared, was just 2 times 10 to the minus 15. That's a very tiny fractional change in the frequency. It's very difficult to measure, but nevertheless, it was verified, this calculation, by making use of some interesting quantum mechanical properties of detectors. There's an effect called the Mossbauer effect, where when that photon of that light, that gamma ray, is absorbed by an atom, well, the atom obviously has to recoil to conserve momentum. But that would give you a big uncertainty because of, if you like, the uncertainty principle. But if that energy that's absorbed is absorbed by all atoms making up that detector collectively, then it can still receive the same momentum, but the given absorption of that will have a less variation to the uncertainty principle. Anyway, long story short, they were able to see this very, very tiny fractional change and see that indeed light changes frequency going up or down a gravitational field.
Picture a wave sent from the bottom to the top. Let the leading edge of the wave mark the start of a time interval, and let the trailing edge of the wave mark the end of the time interval. At the receiving end, the viewer sees that, because the length of the wave has been stretched due to gravitational redshift, the length of time observed is slower than the viewer's clock. The lower clock's time is dilated.
And this is a rocket spring, so it's going to be accelerating. Because it takes a finite amount of time for the light to go from the floor to the ceiling, the rocket will have accelerated in that time. And so its change in velocity will be just acceleration, let's say it's constant acceleration a, times t, the time it took for the light to go from the bottom to top. That's how much the velocity will have changed.